Data structures visualization tools. A deep dive into interactive learning data structures are the building blocks of efficient algorithms and software systems. Understanding them goes beyond memorizing definitions. It requires visual intuition to grasp how elements interact within complex frameworks. In today's digital learning landscape, visualization tools have emerged as indispensable aids for mastering abstract data structure concepts. These interactive platforms transform static theory into dynamic experiences through real-time animations and manipulations. The evolution of data structure teaching methods. Traditional teaching methods relied heavily on textbooks and whiteboard diagrams. While effective for basic understanding, these approaches often failed to demonstrate the nuanced operations of advanced structures like B-trees or red-black trees. With the rise of computer science education online, educators began seeking innovative ways to convey complex ideas visually. This need gave birth to specialized data structure visualization tools that simulate various operations step by step. Interactive simulations allow users to perform insertions, deletions, and traversals manually. Real-time animation show how memory allocation changes during operations. Error detection highlight incorrect operations with immediate feedback mechanisms. Educational institutions now integrate these tools into curricula, providing students with hands-on experience before writing their first line of code. The ability to visualize heapify processes or hash collisions makes abstract concepts tangible and easier to retain. Top platforms for visualizing common data structures. Several outstanding platforms stand out for their clarity and depth when demonstrating fundamental data structures. These tools cater to both beginners and experienced developers looking to reinforce their knowledge. Visualgo from NUS stands as a premier choice, offering over 60 different data structures with animated demonstrations. Its interactive approach allows users to manipulate arrays, linked lists, stacks, queues, and trees dynamically. Visualgo.net provides an extensive collection of algorithms alongside its data structure visualizations. Users can observe sorting techniques like quicksort and merge sort while simultaneously seeing how underlying data structures change during execution. Algorithm Visualizer by Timothy Gralot offers a clean interface where each operation is clearly explained. It supports common structures such as binary search trees, graphs, and priority queues with intuitive controls. DataStructureVisualizations.com presents another excellent option with a strong emphasis on educational value. Its platform includes detailed explanations for every demonstrated concept, making it ideal for self-paced learning. These platforms not only showcase standard implementations but also highlight edge cases and performance characteristics. Students gain insight into time complexity analysis through direct observation of operational costs. Understanding core data structures through visualization tools break down complex structures into digestible components. By watching array indexing happen step by step, learners develop better spatial awareness regarding memory management. For linked list operations, seeing nodes being created and connected helps understand pointer mechanics in action rather than relying solely on theoretical descriptions. This tactile engagement enhances retention significantly. Stacks and queues become more comprehensible when observing LIFO and FIFO principles through animated push/pop operations. Visual confirmation reinforces conceptual understanding without overwhelming the learner. Binary tree traversal becomes less intimidating once users see pre-order, in-order, and post-order processes unfold frame by frame. Seeing recursion in motion demystifies otherwise confusing implementation details. Graph representations benefit immensely from visual representation too. Watching BFS and DFS algorithms navigate through nodes provides instant comprehension of pathfinding logic. Advanced concepts made accessible with animation handling complex structures like heaps and balanced trees benefits greatly from animated walkthroughs. Observing the sift-down process in a minheap reveals why certain properties maintain efficiency in priority queue implementations. Red-black tree rotations come alive through visualization, showing exactly how color changes propagate during insertion and deletion operations. This dynamic display clarifies what might otherwise be confusing textbook illustrations. Tree structures become much clearer when watching character insertions build up word patterns visually. The branching nature of trees shows instantly how they enable fast prefix searches compared to other dictionaries. B-tree operations demonstrate disk access patterns effectively. Seeing splits and merges occur during insertion helps explain why these structures excel at managing large datasets efficiently. Hash table collisions receive special attention in many visualization platforms. Animated probing sequences show linear, quadratic, and double hashing strategies in action, revealing trade-offs between collision resolution methods. Practical applications of visualization in algorithm design. Experienced programmers use these tools to refine their algorithmic thinking before implementing solutions. Observing bubble sort versus merge sort side by side highlights clear differences in performance characteristics. Designers working on distributed systems find hash map visualizations invaluable for optimizing cache eviction policies. Watching least recently used (LRU) algorithms in action informs better architectural decisions. Game developers benefit from graph traversal visualizations that demonstrate shortest path finding algorithms. Seeing Dijkstra's algorithm unfold in real time improves level design choices. Maintainers of large-scale databases utilize B+tree visualizations to optimize query performance. Directly witnessing node splitting during inserts ensures optimal index configurations. Security researchers analyze cryptographic hash functions using visualization tools that track input transformations. Seeing collision resistance materialize through visual demonstrations strengthens security protocols. Building custom visualizers for specialized needs. While existing platforms cover most needs, some professionals require tailored visualizations for niche applications. Building custom solutions enables precise control over what aspects get emphasized. Web-based visualizers can leverage JavaScript libraries like D3.js or 3.js to create interactive three-dimensional models of complex structures. These allow manipulation across axes for deeper exploration. Academic researchers developing new data structures often implement custom visualizers to test hypotheses. Real-time feedback during experimentation accelerates discovery cycles significantly. Industry teams working on machine learning projects sometimes build visualizers for tensor operations. Watching matrix multiplications unfold provides crucial insights into computational bottlenecks. Custom-built visualizers also help in documenting legacy systems. Annotating historical data structures with visual guides preserves institutional knowledge for future reference. Evaluating the effectiveness of different visualization styles. Various visualization styles exist, each suited for particular learning objectives. Choosing the right style depends on whether the goal is conceptual understanding or practical implementation skills. Static diagrams serve best for foundational knowledge where movement isn't necessary. They're useful for explaining abstract relationships between different data types. Animated walkthroughs prove essential when demonstrating sequential operations. Watching a radix sort rearrange digits position by position makes its methodology crystal clear. Interactive simulations foster active learning by letting users experiment safely. Trying different scenarios builds problem-solving capabilities without risking system stability. Hierarchical views work well for complex structures like n-ary trees or multi-level indexes. Layered perspectives reveal internal organization effortlessly. Sidebar annotations complement visual displays by providing context-sensitive information. Explaining Big O notation alongside visual examples creates stronger conceptual links. Future directions in data structure visualization technology. Ongoing research explores integrating augmented reality, AR, with traditional visualization tools. Imagine manipulating 3D linked lists in midair using gesture recognition technology. Artificial intelligence could personalize visualizations based on individual learning preferences. Adaptive interfaces would adjust complexity levels according to user progress and engagement metrics. Virtual reality environments offer immersive learning opportunities where students can physically explore data structures in simulated spaces. Walking through a tree with avatars might make language processing concepts more relatable. Cloud-based collaboration features will enable real-time co-editing of visualizations among remote teams. Sharing development sessions through shared canvases promotes collective learning experiences. As hardware advances continue, we may soon see holographic projectors displaying data structures in actual physical space. Such innovations could revolutionize how we teach and learn computer science fundamentals. Conclusion data structure visualization tools have transformed how we teach and learn fundamental computing concepts. Their impact extends far beyond classroom settings into professional development and research domains alike. To maximize learning outcomes, choose tools that align with your goals, whether you're preparing for technical interviews or designing next-generation algorithms. Engage actively with these resources to unlock true mastery of data structures.